Okay, that was the main thing. We started doing the saver process. Just gonna we make ammonia. Okay, so we did rate of reaction, we did equilibrium, or उसके अंदर ना we have to learn these two processes. So the manufacture of ammonia. That's one, a very important chemical compound because fertilizers are made out of it. Okay, fertilizers are something that's made in a huge quantity in the world because everywhere there are crops being planted. So you also make nitric acid explosives out of ammonia. So the reaction is kind of simple. Okay, it's an exothermic reaction in the forward direction. N2 and H2 react and they produce ammonia. These are the conditions of the reaction. The first thing that they're going to look for is where do you get N2 and H2 from? So N2 is obtained from liquid air. H2 is obtained from cracking of oil or electrolysis of water as well. And these two gases, N2 and H2, they're put in a container and a reaction is started. But the reaction has a really bad yield, which means that since it's a reversible reaction, what happens is as soon as ammonia is produced, a lot of that ammonia actually changes back into N2 and H2. So it's got a very bad yield because not a lot of ammonia is produced in the reaction. So this is why the reaction has a terrible yield because it's a reversible reaction. The ammonia is constantly cooled and liquefied and removed as soon as it's produced, and the rest of the unreacted gases are recycled and they're put back into the container and the reaction is started. It's started again. Okay, Sadeem, is this clear?
Yes, sir.
So now the other thing was you had to justify the conditions. Like, why do you use these conditions? It is a reversible reaction. So the question is, why do you use these conditions, specifically these conditions for the reaction? So justifying conditions was that that the problem with using a higher temperature than this is that higher temperature, according to the equilibrium, according to Lee-Shatler principle, it favors the endothermic reaction, which in this case is the backward reaction. So the yield or output would decrease and less ammonia is going to be formed. Why don't you lower temperature? Lower temperature favors exothermic reaction, which is the forward reaction, which is a good thing. Yield would increase, but at a lower temperature, we know that the rate of reaction is a lot slower. Okay, you have a lot slower reaction. So lowering the temperature would favor the exothermic reaction, forward reaction, but it will take a longer time. So hence temperature 450 is kind of a mid, it's something that's in the middle. So why don't you use a higher pressure? Because at higher pressure, equilibrium favors the less gas mole side, which is the forward reaction. More ammonia is going to be produced. If you look at the reaction, this side is more gas, 4 moles. This side is less gas, 2 moles. So higher pressure always favors the less gas side. So you get more ammonia gas. So at high pressure, particles are closer, you get a faster reaction. You also get more ammonia. The only problem with using a higher pressure is that it's expensive and costly because maintaining a higher pressure is really, really difficult. It is very difficult to maintain a very high pressure. Vice versa, a lower pressure, what's wrong with lower pressure? Because the yield decreases. More gas pole side backward reaction is favored and you get a much slower reaction. So lowering the pressure is not a good idea. I mean, higher pressure is a good thing. The only thing is that it just makes the things very expensive because all the containers, they would have to be made from really thick steel reinforced walls so that it doesn't explode, because higher pressure, that's kind of explosive. It's very hard to maintain a higher pressure. And the catalyst was added because you're supposed to get a faster reaction at a lower temperature. So you have to justify conditions based on the rate of reaction and based on the equilibrium yield of the reaction. Is this clear? Seem clear?
Yes, sir. Thank you.
So the next one is another process that has to be remembered mostly. It's and this other one is this one is a contact process. Okay, just a second. So contact process, what is the contact process? Now it's a process that's used to make sulfuric acid. So you make H2SO4 this way. So how do you make H2SO4 in the first place? I mean, there's three reactions which you have to do. First thing is sulfur is roasted in air. So sulfur is roasted in air. What that means is sulfur is burned in air. It reacts with oxygen to produce sulfur dioxide. So it's an exothermic reaction. Sulfur is burnt in air. Where do you get sulfur? Sulfur is obtained from various sources. Sulfur as a raw material is present in a lot of fossil fuels. Like if you burn coal, that's got a lot of sulfur in it. So as a raw material, it's present in lots of in fossil fuels. That's it. So that's where you get your sulfur. That's the first reaction. And SO2 is produced. Now, SO2 is a very stable compound. In step number 2, what you need to do is you need to somehow turn that SO2 into SO3. So the SO2 is again reacted with oxygen. But this reaction is really difficult because SO2 and SO3 are at equilibrium. So it's really hard to actually make SO3 because as soon as SO3 is formed, the equilibrium shifts backwards. So, I mean, the forward and backward reaction are happening. So turning SO2 into SO3, that's kind of difficult. So you would need a few things for this reaction to happen. You need a catalyst, a V2O5 catalyst is required. The reaction has really high activation energy. You need high temperatures. 450 degrees centigrade is the temperature that's used. Now, all of this stuff you have to remember, and you also need some pressure as well. 2 to 3 atmosphere pressures. Pressure is needed. And this particular reaction is also an exothermic reaction in the forward direction. The enthalpy change is negative. It is exothermic. So in the forward direction, the reaction is exothermic, which means it releases energy. In the reverse, it's going to be the opposite. So once SO3 is formed, what you have to do is turning SO3 into sulfuric acid. The problem that comes or happens over here is that when you try to turn SO3 into sulfuric acid, SO3 can be reacted directly with water. And when you need 2 to 3 atm pressure, This is 2 or 3 atm pressure. ATM is atmosphere. Like, I mean, the pressure that we exist in, 1 atmosphere, that's 1 atmosphere.
Okay.
So turning SO3 into sulfuric acid, what you can do is you can react it directly with water. It will turn it into sulfuric acid. The only problem with this is that this is a very explosive reaction. And exothermic reaction, a lot of heat is produced. So you can't really perform this reaction industrially. I mean, you can't do this reaction in a factory. That would be very dangerous. So can't perform the reaction industrially. So this particular reaction, like dissolving SO3 in water, that just simply makes sulfuric acid. But this reaction is not carried out and is avoided. So instead, what they do is they do another thing, and that is that so instead, what is done is that SO3 is mixed with concentrated sulfuric acid. So what you're basically doing is to make sulfuric acid, you're using sulfuric acid. So SO3 is mixed with concentrated H2SO4. You can remember this one is concentrated H2SO4. It's mixed with concentrated H2SO4, and that turns it into a substance which is known as oleum. OLEUM. Oleum is formed, and in the next step, oleum is then diluted. You add water to oleum. So you take the H2S2O7, which is oleum. You add water to it, and as a result, 2 molecules of H2SO4 are produced. And that's how you get sulfuric acid. So now you have to learn the whole process. Like there are 3 steps involved. The first step was that sulfur was roasted in air, burnt in air, and sulfur dioxide is produced. Most of the sulfur that you're getting, you get it from coal, fossil fuels. There's another ore which produces. I mean, there's some ores as well. Like zinc blende. I mean, it's a compound that's present in a rock that has sulfur in it. So that sulfur is burnt, roasted in air, sulfur dioxide is produced. And then you try to convert the sulfur dioxide into sulfur trioxide, which is kind of difficult. You need some conditions for that. You need V2O5 catalyst, 450 degrees centigrade is the temperature, and 2 to 3 atmospheres is the pressure that's needed. And that's a reversible reaction. That's the only reaction that's reversible. And finally, once you have SO3, you have to turn it into sulfuric acid. Reacting directly with water is kind of dangerous, pretty explosive. So avoided in industries. So instead, they mix it with concentrated sulfuric acid. And when they mix with concentrated sulfuric acid, you get oleum. Oleum is then diluted to form sulfuric acid. So you can see over here that the sulfuric acid that you were using was 1 molecule, and the amount of sulfuric acid that is produced is twice the amount now. So you just used a little bit of sulfuric acid to get a bit more of sulfuric acid. So that's the whole process which you have to memorize, exactly like the Haber process. And that's about sulfuric acid, the manufacture of sulfuric acid. We can talk about the uses of sulfuric acid. So uses of H2SO4 are many. I mean, number one use is that is frequently used as acid in batteries. And it's also used to make fertilizers. So these are some of the main uses of sulfuric acid that we have. Okay, so the whole process, just like the Haber process, these two processes they need to be memorized. Haber process is a lot simpler. Not that many steps involved. You need to know where the raw materials are coming from, and it's got a terrible yield. Now the other thing about this is you have to about the whole contract process. You've got to justify these conditions. The one that we wrote over here. Why are we using those conditions? We'll do the limestone cycle. It's not a cycle. It's basically 1 second. Anyway, so this one, we've got to justify these conditions. So I don't know why. And this part is exactly the same as what we have done in the Haber process. Like how do you justify the conditions? First thing, why don't you use a higher temperature? What's wrong with using a higher temperature? Now the problem with using a hello. अब आ रही है आवाज?
Yes, sir.
Hamza, can you hear me? Hamza, hello.
Yes, sir. Yes, sir.
Sorry, just a second. हाँ, अब आवाज आ रही है?
Yes, sir. Now it's fine.
So ठीक है. अच्छा, so remember कि higher temperature favors it's good thing it speeds up the reaction. ठीक है, ये हमने rate of reaction में पढ़ा था कि kinetic energy speeds up. But the problem with equilibrium is that it favors the endothermic reaction, which in this case is the backward reaction. So you don't want the reaction to go in the backward direction. So the yield would decrease. So which is why we don't use a temperature that's higher than 450. So what's wrong with using a lower temperature? The lower problem with lower temperature is if you lower the temperature, then the good thing is that the exothermic reaction is favored. So your exothermic reaction is going to be favored, which is the forward reaction. Okay, that's the reaction that's going to be favored. Your yield would increase. Okay, the exothermic is the forward reaction. More product would be formed, more yield, higher yield. Now, the only problem with that is that if you lower the temperature, the rate of the reaction drops. So that's a good thing. But the problem is that at lower temperature, rate of reaction decreases. तो मसला ये हो रहा है कि रिएक्शन हो तो रहा है, ठीक है, but it's happening at a very slow rate. So which is why you should not be using a lower temperature than 450. So 450 is like a compromise, not too high, not too low as well. Higher करने का फायदा ये कि you get a faster reaction, but the problem is most of the reaction that's being favored is the backward reaction. Lower करने का फायदा ये कि you get the forward reaction favored. ठीक है, it's going to be the forward reaction happening. More products would be formed, but they would form at a slower rate. So इसलिए आप temperature बीच में रखते हो. Is this clear?
Yes, sir.
So apart from that, you have to justify the conditions about pressure. What's wrong with higher pressure? That's again a good thing. Okay, why not use a higher pressure? The problem with the higher pressure is, it is a good thing. You get a faster reaction. Okay, when you increase the pressure, you put the particles closer together. You squeeze them, you compress them. So you get a faster reaction, and less gas mole side is favored, which is this one. So you even get more forward reaction as well. So that is forward reaction. So in both cases, it's a good thing. Higher pressure, faster reaction. Particles are closer together. You're compressing them. You're bringing them together. So you get a faster reaction. They're going to bump into each other a lot more. And also less gas mole side is favored. This side is the less gas mole side. So more SO3 would be formed. The only problem is that higher pressure is expensive. So higher pressure is going to be very, very expensive. And why not a lower pressure? Because the rate of reaction would drop and the backward reaction would be favored. So, the lower pressure is out of the question. No point using so there is no point using a lower pressure. You get a slow reaction. And more gas mole side is favored. Which is going to be your backward reaction. Okay, so remember, you have to remember everything about the contact process and the Haber process. And you need to justify the conditions using two things. One is rate and the other one is equilibrium. Okay, any questions about this? Is this clear? ये वाला जो part है ये तो memorize करना है, ठीक है? This is all the steps that are involved. You just have to memorize those steps, but you have to justify the conditions that are being used. Okay, what's wrong with using a higher pressure? What's wrong with using a lower temperature? So all of this is clear. Yes or no? Is this clear?
Yes.
अच्छा, अब ये कि we can
Yes, sir.
so we can start with the let's start with the rate of reaction worksheet. Yeah, let's do first rate of reaction, and then we'll do the equilibrium worksheet. So starting with this one, let's just pick here. First one. Let's start with the first one. Now, in the first one, the first question, what he's stating is that the following changes can be made to the condition of the reaction between zinc and hydrochloric acid. So there's a reaction that's happening, zinc and HCl are reacting, and it's a metal plus acid, so it's going to produce zinc chloride plus, I guess H2 gas is going to be produced. So if you increase the concentration of the acid, the rate of the reaction, remember, depends on it depends on 5 things. Okay, we did study this over here. उधर हम चले जाते हैं. ठीक है, depends on 5 things. ठीक है, just 1 second, वहां पे ले जाते हैं. So what were those 5 things? Those 5 things were, कहाँ पे पढ़ा हमने rate? यहाँ पे. हाँ. So it depends on 5 things. The thing number 1 is temperature. ठीक है, that's the first one. तो temperature से क्या होता है? Temperature से होता है कि if you have a higher temperature, you get a faster reaction. क्योंकि वो particles जो हैं वो they collide, travel faster, they bump into each other a lot more, and they have more effective collisions. ठीक है. Pressure से क्या होता है कि pressure से if you increase pressure, the particles become closer together. You get more frequent collisions. ठीक है, ये दूसरा factor था. तीसरा factor था solutions का, कि concentration. If you increase the concentration, ठीक है, so whenever you increase the concentration of a solution, you get more particles per unit volume. So they will bump into each other a lot more. There would be more frequent collisions. एक surface area था कि solid lumps, they'll have slow reaction. Small pieces जो हैं वो ज़्यादा exposed होंगे. There'll be more collisions if the particle is broken down into smaller pieces, which would lead to a faster reaction. आखिरी catalyst था. There were 5 factors that we studied. So first one, increase the concentration of the acid. So obviously you're going to get a faster reaction. Okay, so the reaction is going to be faster. Then increase in particle size. Remember, large pieces जो है ना slow reaction होगा. Is this clear?
जी sir.
Increase in
Yes, sir.
उसको crush करके ना powdered banana smaller pieces, that would lead to a faster reaction. You pick a big piece of rock, large pieces जो होंगे, that would lead to a slow reaction. अच्छा, increase in pressure of the system. अच्छा, remember, increase in pressure of the system, it does increase the rate of the reaction, but there's a problem and there's a catch about this one. ठीक है, एक सेकंड उधर चले जाते हैं. अच्छा, मेरे प्रेशर के साथ ऊपर क्या लिखा हुआ है कि it only affects gases because only gases are compressible, not liquids and solids. तो जो प्रेशर वाली बात है, that only applies to gases, which in this case the gases are missing. I mean, you've got zinc and you've got HCl. Both of them are not actually, I mean, they're not gases. ठीक है, तो यहाँ पे वो बात अप्लाई नहीं करेगी. तो इसलिए increase in pressure of the system only applies if there were gases involved. Is that clear as well?
Yes.
So last one is if you increase temperature of the system, that will result in a faster reaction. So इसलिए it's going to be 1 and only 1 and 4. That would lead to a faster reaction. Pressure का याद रखना कि it only applies to gases, not to solids or liquids, because solids and liquids are incompressible. gases के अंदर if you increase pressure, they're compressible. The particles become closer to each other, and you get a faster reaction. अच्छा अगला आ जाते हैं कि ग्राफ्स के बारे में बताया था कि अच्छा ग्राफ्स के अंदर मैंने बताया था the steeper the graph, the faster is the reaction. मतलब with respect to time जो ग्राफ होते हैं ना जैसे ये पहला वाला स्टीपर है तो इसके अंदर वॉल्यूम ऑफ गैस ज्यादा तेजी से प्रोड्यूस हो रही है. It's being produced at a much faster rate. There's a lot more volume of gas being produced. So steeper curve indicates a faster reaction. So initially, which one is the faster reaction? Experiment number 1 or experiment number 2? किसी curve ज़्यादा steep है? Anyone? Wasa, Amna, Saneem? Which one has a steeper curve?
So experiment 1.
Okay, so it's going to be experiment 1. Experiment 1, the volume of H2 gas is produced at a much faster pace. Okay, look at the curve. So experiment number 1, if we go back, experiment number 1 is going to be like if you plot the speed of reaction, one would be faster. So yahan pe bhi na 1 is faster. These two graphs. It's either C, it's either A or D. Achha, but then after some time, what happens? The experiment 1 slows down. Its curve becomes, it's completely flat. So that means the reaction has stopped. But experiment number 2 is still going on. It's still, the gradient is still not flat. It's not 0. So now, after some time, experiment number 2 is the faster one. Experiment number 1 is the slower one. Because experiment number 1 has practically stopped. The reaction has stopped. So after some time, like over here, experiment number 1 comes to a stop a lot quickly. Experiment number 2, like experiment number 1, the reaction practically stopped at this point. There was no reaction happening at this point because at this point, hardly any reaction was going on. Just a second. At 1 second. So at this point, at experiment number 1, the reaction had completely stopped. तो वो पहले रुक गया था. इस टाइम के ऊपर ना the reaction was stopped, and the experiment 2 continued on. So is this clear? The option A is going to be the correct option.
Sir, could you repeat it one more time?
First thing, initially who's fast? Right at the beginning, it's experiment 1, right?
Yes, sir.
So you're plotting the speed. The experiment number 2 is slower, and the reason for that is that your curve is a lot steeper for experiment number 1. But which reaction stops early? Which one, experiment 1 or experiment number 2?
Experiment 1.
Because experiment number 1, the volume of H2 stops increasing at this point. So it stops a lot quickly. So experiment number 1 is faster, but the speed of the reaction goes to 0, or it completely stops a lot early compared to the experiment number 2. Do you get this?
Yes, sir, I get it now.
Experiment number 2 is slower. The curve is less steep, but it goes on for a longer time. Even now it's not coming to a stop. I think there's some H2 gas being produced. So let's do this one. Which graph represents how the rate reaction varies with time when excess of calcium carbonate reacts with dilute hydrochloric acid? It's B. It's the rate with respect to time. Varies with time. with dilute hydrochloric acid. So the rate of the reaction is always faster right at the beginning. मतलब क्या होता है reactions के अंदर? Reactions are very fast at the beginning, and then they start to slow down. ठीक है, so the graph is probably going to look like this. I mean, they're going to be fast at the beginning, and then the reaction starts slowing down. जैसा Coke डालो ना, अगर if you add Pepsi to a glass, you see a lot of bubbles at the beginning. So the reaction or the speed of the reaction is really high at the beginning, and then it starts to slow down. It slows down, eventually it goes to zero. It takes longer and longer time, but the speed of the reaction or the rate of the reaction, it eventually slows down. So you're adding Pepsi to a cup, lots of bubbles produced initially, and then the bubbles, they start dying off and the reaction starts to slow down. Is this clear?
Yes, sir.
As for this one, you've got this reaction. And he's saying calcium carbonate is being added. In experiment number 1, 100 grams of calcium carbonate is added. Experiment number 2, 50 grams of calcium carbonate is added. Pehle to batao which one is going to produce more carbon dioxide? Experiment number 1 or experiment number 2? I mean, which one would produce more carbon dioxide?
Experiment number 1.
Experiment number 1, because you're adding more calcium carbonate. So, so it's going to be 1. So, when I graph dekhe na, so it's going to be, I mean, this is correct, 1 will produce more carbon dioxide. And 1 would produce exactly double the amount. Because आपने जो mass add की वो double add किया. So, it's either going to be 1 में ना 2 के मुकाबले में. Remember, this axis is volume of carbon dioxide. C would be wrong. Because I think इसके अंदर carbon dioxide जो है ना 1 के अंदर 3 times produce हो रही है. So that would be wrong. Double होना चाहिए. So it's either going to be A or it's going to be D. B इसलिए गलत है कि दोनों में same amount of carbon dioxide produce हो रही है. So याद clear है कि it's going to be A and D but not C.
जी सर.
अच्छा हमजा उस पे मैं आता हूँ. अब वो कह रहे कि reaction faster कौन सा होगा? Now I know which one it's A or D, but which one would be faster? Large lumps or fine powder?
Fine powder.
Okay, so fine powder is going to be faster. That means it's going to be steeper. So experiment number 2 जो होगा ना, that would be steeper. तो यहाँ पे अगर आप गौर से देखो ना, तो experiment number 2, ठीक है, if you look closely, तो जो experiment number 2 है उसकी जो line है ना, that's a lot steeper. So if you look closely, और यहाँ पे ना experiment 1 जो है ना, that's more steep. That's steeper. और experiment 2 जो है ना, वो थोड़ा सा slow है. And remember we said that experiment 2 is going to be faster. So if it's going to be faster, so it's going to be D. So Hamza, did you get this?
Yes, sir. Go ahead.
वो एंड में पूरा का पूरा पीस डिसॉल्व होगा, लेकिन आहिस्ता आहिस्ता करके डिसॉल्व होगा. मतलब यहाँ पे ना अगर इफ आई गो अवे है तो वो जो लार्ज लम्प्स वाली बात थी, इसका ये मतलब नहीं है कि अंदर वाला बिल्कुल भी रिएक्ट नहीं करेगा. द ओनली इशू इज कि पहले वो बाहर वाले रिएक्ट करेंगे, फिर उससे अंदर वाले रिएक्ट करेंगे. इट्स गोइंग टू टेक टाइम फॉर द इनर वंस टू डिसॉल्व. तो पाउडर के अंदर ऑल ऑफ देम विल रिएक्ट एट द सेम टाइम. So just remember in this case, experiment 1 में कार्बन डाइऑक्साइड की जो अमाउंट थी ना, वो डबल प्रोड्यूस होनी थी, लेकिन मसला था एक्सपेरिमेंट नंबर 1 इज स्लो, तो उसका जो ग्राफ हो रहा था वो लेस स्टीप होना था. चलिए लेट्स कंटिन्यू विद द सेम थिंग. ठीक है, कल हम कंटिन्यू करते हैं. विल डू इक्विलिब्रियम क्वेश्चंस एज वेल एज रेट क्वेश्चंस. ठीक है, चलिए लेट्स कंटिन्यू टुमारो. ओके एवरीवन,
Love it, sir.
अल्लाह हाफिज.